This video is for the learning map I have done for waves and the Big Bang Theory. This is in P1 part 2 of AQA. So you need to know the different types of waves. So waves can fall into two different categories. First one is longitudinal. Okay, and examples of this would be a sound. I like to say longitudinal like this, so makes a sound. Seismic waves, mechanical waves, so you can say slinky. Now the important bit about this you need to know is that longitudinal waves are a series of compressions and rarefactions. It requires a medium to travel through for it to happen. And a really important key part you need to know is that the oscillations, so the direction of travel, are parallel to the energy transfer. So the oscillations will go this way, and so does the energy transfer, so they are parallel. That's a really important key word there. The next ones you need to know about are transverse, and these are probably the ones you're most familiar with. Now, examples of transverse waves are light, microwave, gamma, mechanical. Again, note that this can be either. That is asked in the exam sometimes. Any EM spectrum wave is a transverse wave. I like to look at it like this, up and down, doesn't make a sound. Now, a transverse wave is a series of peaks, or sometimes they're called crests, and troughs. So you need to know that. And then the important key thing for these ones are that the oscillations, so go up and down, are perpendicular, or you can say at right angles, to the direction of energy transfer. Features of a wave. Now, even sound waves, if they go for an oscilloscope, will look like this, so you can tell different things about them. The amplitude of a wave is the distance from the middle of the wave to the top, or the middle to the bottom, okay, and it's measured in meters. The wavelength of a wave is the distance from one place on a wave to the same place on the next wave. So peak to peak, trough to trough, even here to here. Always try and go peak or troughs because then you're less likely to get it wrong. With this, the frequency is the number of hertz. Frequency is measured in hertz, and frequency is basically the number of waves you get per second. So if there was 2 waves a second, it would be a frequency of 2 hertz. If there was 1 wave in 2 seconds, it would be a frequency of half of a hertz. This can come up and does quite frequently, and usually they use standard form numbers, so please remember your scientific calculator. Wave speed in meters per second, which is V, equals the frequency measured in hertz, capital H, little z, not little h, times the wavelength, which is measured in meters, okay? Like I said, they will usually give you frequency and wavelength as the standard form number, so don't get confused. If we go over to here now, there's different ways in which these waves will, you can do experiments with them, and I have got a separate video on this. The first one is reflection. Now, all waves reflect off of the surface. When they do that, it's really important that you know that the angle of incidence equals the angle of reflection, okay? The incident wave will come in and it will reflect off, and you need to have your normal 90 degrees to the surface. I have a feeling, although I don't know what they're doing this year, so probably won't come up, is they might ask you to maybe do something like this. This can be worth 4 marks, where you have to draw the reflected object within a mirror, okay? So if you're confused about how to do that, watch the video I've done. The next way they can experiment is refraction, okay? Now this means to bend. So when waves come in contact with a medium, a different medium of a different density, they might reflect, but they might travel through it. Now, because they're going from one density to another, their speed changes, so their direction changes. So for example, if you go into a more dense medium, it will bend towards the normal. Less dense medium, it will bend away from the normal. If leaving into the same medium, the exit angle will be the same as the entry angle, so they must be parallel. You get marks for that in the exam. More dense, bend towards, less dense, bend away. The other one that can happen is diffraction. Now, they can lead this to questions about hills and things like that, because they seem to be relating science to everyday life. So make sure you can relate all this stuff to something that might happen every day. Diffraction is when waves come in contact with, say, a gap, and they will diffract through the gap or around an obstacle, and they'll diffract around the obstacle. This is sometimes asked about the level of diffraction. The greatest diffraction is when the size of the gap and the wavelength are same or similar. Okay, EM spectrum waves only came up ever so slightly last year. you need to know this order. So you've got radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma. There is a way you can remember it. There's a rude way, but I'm going to tell you the PC way. Retired monkeys in Vegas use xylophones good. Okay. In the comments, if you want to know the other way, I will put it in. Now, the features of them. So they're talking about features of the wave. They're talking about what does it do, what does it look like. So, for example, you can talk about their energy. As you increase from radio up to gamma, they increase in their amount of energy. As you go from gamma to radio, it increases wavelength. So these will have the longest and these will have the shortest wavelength. Frequency, if it's got the smallest wavelength, it has the highest frequency. So it will increase in frequency. This has been asked before about the speed that they travel at, and they all travel at the same speed through a vacuum, which is 300 million meters per second, okay? Or 3 times 10 to the 8 meters per second. Notice the 10 to the 8 means there's 8 zeros, okay? So you might also be asked about what they do, so their uses and their dangers. So radio waves are used for TV, radio, communications. Not necessarily much dangers with radio waves because their wavelength is so long. Microwaves isn't just used for cooking your food, okay? It can be mobile phones and satellites. And the damage with this is it causes internal tissue heating. So when you put your food in the microwave, what it actually does is it makes the water particles vibrate so much that it creates the friction, which generates the heat. Well, then you're putting that mobile phone next to your ear and it could be doing the same. There's not enough scientific research. So with this one, it could talk about scientific research of mobile phones and whether there is any danger with them and things like that, okay? But yeah, microwave waves are used in mobile phone signals. Infrared radiation, obviously heat emits from everything and absorbed by everything, but it can also be used for remote controls, cable, night vision. The danger of it can cause burns, so it can actually burn your skin. Visible light we use to see, photography, internet actually. Fibre optic cables uses pulses of light for the internet. Did you know that? Dangers of it, it can blind you, so don't look directly at the sun, etc. UV light gives you a nice suntan. It can be used in sunbeds, it can be used in security tagging, and also it can be used to sterilise things from bacteria and so forth. Danger of it, it can cause skin cancer. X-rays, it's quite obvious, we can use for broken bones, metal defects. You can actually use it for some cancer treatments also. But the dangers of it, it can cause cancer. So there's only so many X-rays you're allowed per year. But then when it comes to this one, does the risk of having it outweigh the benefit of diagnosing a broken bone? Well, yes, it does. That's why they give you it. Gamma can be used for sterilising equipment again and cancer treatment, but it can cause cancer also. So cancer, 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 blindness, burn you, internal tissue heating, fine. Sound waves hasn't come up for a couple of years, and people think, I know sound, and then they get the question completely wrong. Sound actually travels best through a solid because sound is a series of vibrations, so if it needs to vibrate through something, it's going to do it through the densest material. It travels through air at 340 meters per second, which is why, did you know, when you get thunder and lightning, they actually happen at the same time. But because light travels at 300 millimeters per second, and sound only travels at 340 meters per second, you see it before you hear it. That's why when it's closer together, you know the storm is near you more. Now, when we come to sound waves, we're concerned with pitch. Now, pitch is all about the frequency of the wave. The higher the pitch, the higher the frequency, and the smaller the wavelength. The lower the pitch, then the lower the frequency, and the longer the wavelength, okay? So high pitch, low pitch, Volume is all to do with the amplitude of the wave, okay? The amplitude. Think when you've got an electric guitar, you plug it into an amplifier to make it louder, okay? Remember, it's just from the middle to the peak. So the larger the amplitude would be a higher volume. The lower the amplitude would be a lower volume. Big Bang Theory, okay? I'm going to go through this one first and I think I'll come back to this one. So the Doppler Effect. So this is Sheldon Cooper's way of saying it. I do know it off by heart. It's the apparent change of the frequency in the wave caused by the relative motion between the source of the wave and the observer. Basically, apparent means it doesn't actually happen. When you say, oh, apparently she said that, did she really? Have you got proof? No. So apparent means it doesn't actually happen. Now, it's in the frequency of the wave, so to do the pitch. So apparently the pitch changes, and it's caused by the motion between the thing making the sound, the sound source of the wave, and the person listening, the observer. So it's all to do with the motion between the thing making the sound and the person listening to it who's stationary. It appears to change. And if you have a look here, if a wave source was stationary, no matter where you stand around this wave source, you're going to hear the same pitch. The further you get out, the volume will decrease because of the energy being lost, but the pitch would be the same. However, if you start moving really, really fast towards that person, and you imagine these are circles that can't actually can't deform, as you go forward, these are going to become compressed, okay? So the gap between them is going to get smaller. If the gap between gets smaller, you're talking about pitch, you're talking about frequency. A higher frequency, which leads to a higher pitch. So this is why things coming towards you sound really high pitched. And when they go away from you, the waves are spread out. So they're no longer compressed, they're spread out. And because they're spread out, you're going to get a lower pitch. So coming towards you, past you. However, the thing making the sound wouldn't hear any change whatsoever because they're not moving relative to themselves. So they would hear just a constant pitch. So that's why it's just a phenomena that appears to happen, but it doesn't actually. Redshift is basically what happens in sound, happens in light also. So when the Big Bang happened, we think that everything was at one initial point. Basically, we've noticed that galaxies moving away from us, their spectral absorption lines. Now, what I mean by this is you have stars, you might learn about in P2, and they consist of certain elements. Now, certain elements will absorb wavelengths of light. So it becomes like this little barcode type thing. It's called spectral absorption lines. So you have an unshifted one, so it's just normal. And then when it gets, say, blue shifted, it means it's gone that way. So it means the wavelength will have decreased. So that one we say is coming towards us. And redshift, they're getting further apart, they're getting spread out. So we say it's going away from us. And this is all to do with the fabric of space and time expanding. So again, like that, not really happening, just appears to be happening. The way I ask my class to remember redshift is a bit corny, really. Imagine you've got your mates around you and you see someone you really fancy. So you act all like cool and calm and like blue coloured. And you go over and you say, do you fancy maybe going to Nando's tonight? And then you get rejected. So what you're going to do, you're going to go all red-faced and you're going to run away, okay? And the more embarrassed you are, the more red you're going to get. So the faster you're going to run. And that leads you on to Hubble's law. Hubble's law means the greater the redshift, the faster that galaxy is actually moving, okay? So blue going towards, red running away because you're embarrassed as hell. So how does this lead on to the Big Bang? Okay, so the Big Bang is just a theory. We can't prove it, we've got evidence, but it's our best guess, really. So it's a theory of how the universe was created. Please do not say the Earth or the world. It is the universe. They might also ask you, what is the universe? It's all of the galaxies, okay? Now, we think that everything in the entire universe was at this one hot, dense initial point, okay? And then an explosion happened. Don't know what caused it, but an explosion happened. That's the moment time began. And ever since then, the universe has been expanding ever outward. Fat person, waistline. And evidence that we have for this is redshift. So why would we be observing things moving away from us? Like in all directions. They must have started at one initial point. And another thing we use is something called cosmic microwave background radiation, CMBR. Now this is when this initial explosion happened, there was so much heat, infrared radiation, and as the fabric of space of time is expanding, it has increased the wavelength. If you increase the wavelength from infrared, you go to microwave. So we're observing this microwave radiation all around us, and that's our best guess where it's come from. And they do think in time, maybe it will expand further and it will become radio waves. They could also ask you theories about what will happen. And then something called the big crunch or the big chill. So the big chill is that everything gets so far apart from each other that even sources of light can't help life, and then everything just sort of cools down, stops expanding. Or the big crunch is that gravity will put everything back in together, and we think then maybe there'll be another Big Bang. Does that leads you to think, how many Big Bangs have that actually been? Try not to think about it, it will make your head hurt. Okay, I hope that helps.